So now I'm going to show you some of the calculations that we do on the plane to calculate the vector. Our first set of equations here are for going from a geodetic coordinate system to a geocentric coordinate system. Geodetic is latitude and longitude. Most people are familiar with it. What we do is we take into account the fact that the Earth is an ellipsoid. And this is important for our application because not only is the degree of latitude different at different north and south, but a degree of longitude is also different because of the eccentricity of the Earth. So what we do is we calculate a normalization using A as a primary, A is the semi-major axis of the Earth. That's the radius of the Earth from the center of the Earth to the equator. And then use the eccentricity of the Earth, and the phi is the latitude that you're at, and that's a normalization. Then x, y, and z are your geocentric coordinates for any latitude and longitude. These are intermediate steps for calculating x, y, and z. But once we have an x, y, and z of both the plane and the target, we now have in meters our distance to the target with in a geocentric coordinate system. Geocentric means that the center of the Earth is the center of the universe. That's our origin. Z points up through the North Pole, X points out through the prime meridian, and Y is orthogonal to that in the right-hand rule. So once we have our geocentric coordinate system, what we want to do is we want to go to a local Earth level coordinate system because it's not very useful for us to talk about the Earth as a sphere like that. It's only useful for us to take out the eccentricity of the Earth. So we just do a simple rotational transform. You multiply these two matrices, and you get the location of the plane in terms of x, y, and z from the target, where x is due east, y is due north, and z is straight up. We assume that for our application, which is distances of less than 10 kilometers, that the Earth can be treated as a level plane, and this works out pretty well. Finally, we want to calculate the vector for pointing the gimbal. We use just a spherical coordinate system to point the gimbal. We need to pull out our theta and phi, where theta is the angle along the xy plane, and phi is the angle coming down off the z-axis. It's important to take into account our roll, pitch, and yaw. So what we do is we calculate intermediate rho and a gamma. That's the projection of the x and y. That's projection onto the xy plane and onto the projection onto the zy plane and onto the zx plane. What this allows us to do is that roll is a roll around the x-axis. So the zy plane is only affected by roll. Pitch is a rotation about the y-axis. So the zx plane is only affected by pitch. So what we can then do is we can correct for roll, then correct for pitch, then solve for theta and phi. These calculations are done using floating point numbers, and they're done in the background of our control program. Now I'm going to hand off to Victor to show you some of our experimental results.
All right, my name is Victor. Here's our first video download test slide. We set goals before we do the test slides. In this case, our purpose was to test our video downlink and log GPS data. As you can see here, we are required to use our call sign because we are transmitting 1200 megahertz at over 1 watt. On board, we have the 1200 megahertz NTSC video downlink, as well as the 2.4 gigahertz radio controls. As you can see here, the way we have our video downlink mounted on the plane, there's an instance where the video downlink and our radio controls get aligned, and we get a second harmonic interference, and we lose control of the plane for a few seconds. Then we regain controls. The pilot was able to land it safely because we ran out of the runway and landed on grass. This is our flight path for the crash. You can see here. So we go around, control, and right over here, we make controls in over here. This is done on Google Earth, and our GPS data, which is a CSV file. This is a different test flight. The purpose of this one is to, as well, test our login mechanism and be able to paste it on Google Earth. This is not the whole part of the flight path. It's supposed to be a west part of it, but because we were on a tin roof building, we were getting interference of this angle right here, and so we lost some of our data. So one of the advantages of Google Earth is that so we identify this kind of issues that we didn't before. So this is a great tool to identify this kind of problem. Next, Fred is going to explain us about the gimbal system.